Okay, so sorry for the for what just happened. I try to, as I said, I'm trying to record all my lectures because first of all, some students they cannot come to this class because of the course conflict, and second of all, some students they do not come to the classes even though they can. So, but today somehow the Zoom has some problem. So I'm using just PowerPoint to do this recording. Hopefully it works. Okay, so let's just continue with what we have left from Monday's lecture. So in Monday, we basically talk about for a absorption tower, some like very important concepts for us to analyze the absorption tower. One of them is that we know in the tweed absorption tower, liquid absorbance flowing down, whereas the vapor gas phase going up, right? Then they will mix in each tree, and when they mix in each tree, the solute will transfer from the gas phase into the liquid absorbent phase, right? And basically the whole design of an absorption tower is basically to figure out if we want to achieve a certain separation outcome, right? Then first of all, what are gonna be the liquid absorbance flow rate, right? Given a vapor or gas phase flow rate, right? That's our phi. How much? That is to say, how much liquid absorbance do we need, right? And the second question is for tree towers, how many trees do we need, right? Those are kind of two questions we need to answer. For the first question, like how much liquid absorbance we need, we can solve that by just mole balance, right? And in order to simplify our mole balance derivation, we just assume in each tree, the liquid absorbance mixed with the gas phase sufficient long so they reach equilibrium, right? And that just help us to, so we don't have to consider, the details of the mass transfer in each tree. That will greatly simplify the problem. Then by doing that, we can derive a operation line equation, right? This equation basically, if given phase composition x0 and yn plus 1, right? So this equation basically given x0 and y1, right? That's basically the composition of the liquid absorbance coming to the tower and the composition of the gas phase leaving the tower. And if we know the vapor flow rate and the gas flow rate, the vapor flow rate and the liquid flow rate, right? Then from this equation, basically it relates yn plus 1 with xn, right? And that's basically the composition of the liquid stream and the gas phase leaving and entering stage n, right? Then we can extend this to the last stage, the nth stage, right? That can relate the composition of the incoming gas phase and the exiting liquid stream. So basically there are as you can see, 6 variables here in this equation. So as long as we know 5 of them, we should be able to figure out the last one. Right? So one example is here. If we know the phase stream compositions, right, that's x0 and yn plus 1. We know the gas flow rate, that's v prime. And we know xn and y1. Xn and y1. Let's find solvent flow rate, right? The only one that's missing is this one. The 2 ways you can do this: either you can just plug in the numbers into this equation, and you can solve for L prime, or graphically, we can do this graphically, by first, identify the points. Here we know the phase stream composition and x and y1. That just give us the coordinates of the 2 ending points for the operation line, right? This line and that line, and this point and that point. And if you connect these 2 points, that give you a straight line whose slope can be measured. And we know that the slope is the ratio of v prime over L prime, right? And L prime is v prime is known, and you can just solve for L prime. Okay, that's one case. Another example is we know the phase stream composition, and we know the flow rates and y1. Let's find out xn. Okay, so in this case, we know phase stream composition and y1 that give us the coordinate of this point, right? And we know the flow rates of the liquid and vapor phase that give us the slope, right? This slope, right? Then we know the phase stream composition that tell us yn plus 1, right? We can draw a vertical line, a horizontal line here. Then this straight line will basically cross with this operation line at this point, right? And from the axis coordinate of that point, we can find out xn. Right? So this is another example in which we know the feed stream composition, flow rates, and xn. How do we find y1? Right. Similarly, from feed stream composition, you find the coordinate of this point, right? And from flow rates, you find the slope, right? Then basically x0 is given, right? That's feed stream composition, one of the feed stream composition. You can draw a vertical line here. Then basically this operation line will cross with this vertical line at one point, and the y coordinate of this point gives you the y1, right? That's the composition of the exciting gas stream. Okay, so basically these 3 examples is just to show you that once we know the operation line, and basically and you were given the value of 5 variables in the operation line, then you can solve for the rest, for the last one. Okay. Then that leads to a question. Okay. So now let's look at this concept, minimum flow rate. Typically, for absorption tower, right? We know that the yn plus 1, that's the feed composition of the gas stream, right? That's from your reactor, right? That's before your separation unit. And we know the composition of your incoming liquid absorbance, right? And that's something we control. And we know the vapor phase flow rate. That's again from your your reactor. That's before your separation unit. We know that. Now we want to design a absorption tower to achieve a desired y1, right? That is to say, we want to make sure when the vapor phase leaving this absorption tower, the solute composition will decrease to a value of y1, right? Now we have we know the 4 variables. There are still 2 variables, right? Now basically, if these 2 variables, if we know one of them, then the other one is determined, right? So if we know the liquid absorbent flow rate L prime, then we can solve for xn, right? So then there are many different cases for the liquid absorbent flow rate. You can pick like very large liquid absorbent flow rate, right? That's infinite liquid absorbent flow rate. So in this case, it's like you just gave the absorption tower an infinite amount of liquid absorbance. So then you have this line crossing yn plus 1 at this point, right? And that point gives you the composition of the exciting liquid stream, which with a composition x0, right? Xn equals x0. Right? That means basically if you have infinite amount of liquid absorbance getting into this tower, when they leave the tower, their composition just doesn't change because it's so much of them there, and even though some solute gets transferred from the gas phase into the liquid phase, it just doesn't change its composition because you have infinite amount of liquid absorbance, right? So obviously that's not practical, right? So in reality, we use a finite amount of liquid absorbance fluid, right? That will basically change the slope of this line from vertical to some finite slope, right? For example, on this operation line 2, right? Now, once we define L prime, we define the slope, then this line cross with yn plus 1 at this point. Then, as we just discussed, if you draw a vertical line here, right, then we can figure out the composition of the exciting liquid stream. Okay, to reduce the operational cost, we want to say, okay, let's use as little liquid absorbance as we can, right? That will greatly reduce the operational cost. Then we can just keep reducing L, right? Then the slope of this line, operation line, will also reduce. But eventually it's gonna cross the equilibrium curve at this point, right? That is the minimum flow rate, because at that flow rate, your liquid absorbance will be saturated when they exit the absorption tower, right? Because if you if you further reduce, let's say further reduce the flow rate, right, then you will get a line that's below this line. Then that line will cross yn plus 1 at this point here, and that is a composition beyond the equilibrium curve, so it cannot be achieved. Okay. So then from this equation we can just derive L prime, right? Just basically you move a y1 to the left, then you divide x and minus x0 to the right, then you multiply the equation by v prime on both left and right hand side, so you can get L prime, right? So then we can compute the minimum flow rate that is required for the absorption tower to operate, which is that at the minimum flow rate, right, this point, the x coordinate of this point can be read from the equilibrium curve. Then you can just plug in, that value with x0, yn plus 1, and y1, those are given. Then you can compute the minimum flow rate, right? And again, the solute concentration in the exciting liquid xn, that depends on the flow rate. Flow rate, as you change the flow rate, you will change the slope of the operation line. Then where they cross this yn plus 1 horizontal line will change. Then you change basically the composition of the exciting liquid stream. So now, question. What would happen for a flow rate that's even lower than the minimum flow rate? Any guess? Francis?
I said, absorb anything, right?
I'm sorry?
Nothing would be separated.
So you won't achieve your separation outcome, yeah, right? But specifically, let's say let's further reduce the liquid flow rate to below an amount of minimum flow rate, right? Then we'll end up with an operation line that's below this minimum one. Okay. Then we know that then this operation line will cross equilibrium curve at this point. It cannot go beyond that point, right? Then that will be beyond equilibrium, beyond thermodynamics. Then if we draw a horizontal line here, then we will figure out, if you do this, basically that's your kind of like an incoming gas composition, the maximum gas composition. You can achieve a desired separation outcome of Y1, right? If you feed a gas feed with this composition, then you won't achieve this separation outcome. The maximum you can do is this composition. Okay. Now, so here we have the you know, that's from the operation line we can derive L prime, right, to be this, and we know now we're trying to we are going to compute the minimum flow rate, right? Because that's a kind of very important parameter when we design a absorption tower. We need to figure out what is the minimum first. Then we can say, okay, maybe we can give a flow rate that's twice as much or 3 times as much, right? That gives us a starting point to pick how much liquid absorbent flow rate we use. Okay. And to do that, right, first we from the operation line we can derive L prime to be dependent on the the composition of the feed and the exit streams, as well as the vapor flow rate. And meanwhile, for our operation, we know the composition of the this is the incoming gas. This is the composition of the gas phase. Of the gas feed, and this is the composition of the liquid feed, and this is the desired separation outcome, right? We don't know this one, but we know at the minimum flow rate, the operation line cross the equilibrium line, so that xn is related to yn plus 1 by the key value, right? And if we rearrange this equation, then we can derive xn, we plug xn into that, we can get L min to be this. Okay. So let's see if we can do that here. So here, okay, again, the idea is to rearrange this equation, right, to get xn. Then we can plug xn into this equation. Then you can get L prime min, right? So how do we do this? Okay, sorry. Okay, let's see. How do I do this? This minimum impact. Okay. So first thing we do is that now we see the xn is at the denominator, right? So the first thing we do is just to put it back as a numerator. Then we can just take the inverse of this equation. Then we can have xn plus divided by 1 plus xn, right? Then well, you divide by this whole term, but we can just move the whole term to the right. So we have kn multiplied by this term yn plus 1 divided by 1 plus yn plus 1. Okay. So next thing is that now we have xn on both the numerator and the denominator, and we just want to reduce that. The way we can do that is just by minus the whole thing with divide this whole thing with 1, right? Just divide up, sorry, like subtract 1 from both sides, right? Now on the left hand side you will have so we can do 1 minus, right? Let's do 1 minus this term plus, and on the left, and 1 minus this term on the right. And on the left we will have 1 plus xn 1, right? Now because you have 1 plus xn on the numerator minus xn, that give you 1. On the right hand side you will have let's see, we can just plug in xn here. We can plug kn here, 1 plus yn plus 1, right? That's on the denominator. Then above the fraction line we have kn 1 plus yn plus 1 minus yn plus 1. Okay. Then you take again, you take the inverse of this whole equation on both left side and right hand side, right? You get 1 plus xn equals kn Now we can rearrange this term a little bit, right? So we have, let's do this. We just organize all the yn terms together. We have yn plus 1. Then we have kn minus 1, right? Because we have yn here, and we have kn multiplied by yn plus here, plus kn yn plus 1, right? That's on the, we are flipping, because we're taking inverse, so we are flipping the numerator to be the denominator, okay? So then above, we have kn plus kn yn plus 1, okay? Now, next thing you do, just, subtract 1 on both sides. On the left, you have xn. On the right, so you have yn plus 1, kn minus 1, plus kn yn plus 1. Okay, then we have 1 of that's going to be this whole term minus this whole term. Let's see what is that. Okay, so so we're going to have kn plus y multiplied by yn plus 1 minus that's going to be cancelled, and so we're going to have yn plus 1. Okay, so then I think we have this one now, right? Because basically you just replace xn equals this whole term. Okay, yn plus 1 divided by this whole term. Okay, now we have it. Okay, good. Now we derived the minimum flow rate. That's going to be dependent on a function of all the known values, right? We know V prime, that's the vapor phase flow rate. We know yn plus 1, that's the gas phase. That's a fate composition of the gas phase, right? We know y1, that's our desired separation outcome. And we know Kn, that's key value, that's from equilibrium data. We know x0, that's the composition of the liquid, the incoming liquid stream. Right? We know all the values, then we just plug in, we can compute L min, right? And we can even further simplify this equation under some conditions. And typically, if we have a dilute solid, right? That means x. Mole fraction of x and y mole fraction of the solid in both the liquid and vapor phase are small, right? And if you look at this equation, if x and y are small compared to 1, then here the denominator will become 1, right? So we have the molar ratio to be approximately equal to the mole fraction, right? Basically, like capital Y equals approximate, lowercase y, and the same here. Then you can just convert the capital Y and n here to lowercase y and n. Okay, and another thing, just convert this to that, y1 to y1 here, and x0 to x0 here. There's one more thing we need to do before we simplify and get this equation, which is that if you look at this term, right? If y is small, if y is small, then this term vanishes, right? We have only Kn. That's why we have only Kn here. Okay. Further, if for the entering liquid, right? If we for the entering liquid, it does not contain any solute, or the amount of solute in the entering liquid is very minimum. Then we have the mole ratio of x0 to be approximate 0, right? So in this case, then that's 0 as well, and that will be 0 as well, right? And in this case, yn plus 1 and yn plus 1, they basically cross. then you have only L prime mean equals V prime multiplied by Kn. Right? So in this case, the minimum flow rate is so simple. It's only dependent on the vapor flow rate and your equilibrium K value, right? And obviously, in this case, if you increase the vapor flow rate, then you need to increase the minimum flow rate to achieve the same separation outcome. Okay. Now, in the derivation in last slide, basically we know for a given absorption task, right? If we for a given absorption task, basically we know the feed composition, we know the desired separation outcome Y1, and we know the gas flow rate, right? That's our feed flow rate. Then we know what's the minimum liquid absorbent flow rate to achieve the desired separation outcome Y1. But in reality, we don't operate at the minimum flow rate. We operate at a higher flow rate, right? Then the question becomes, how many equilibrium stages do we need to achieve the desired separation outcome? So we're going to answer that question in this slide. So we have the absorption tower here and the stage 1, right? So we have we know the composition of the liquid absorbents coming in. We know the desired, Y1 is our desired separation outcome, right? That's the composition of the exiting gas phase. We also know Yn plus 1, okay? And from equilibrium data, we can get the equilibrium curve. And once we specify the liquid flow rate, right, L prime, then we can draw a operation line, right? Again, we know this point, and we can draw, if we know the L prime and V prime, we can draw this operation line, right? And we know that that's our, the composition of the gas stream coming into the tower. Okay? Now, how many equilibrium states do we need to achieve this desired separation outcome? Okay. The way we do this is by a so-called, step operation. Now we have these two lines. Now we can start from, this point, right? That point, we can start from this point on the operation line. Right? Recall this point is basically the composition above the first stage in our, absorption tower, right? Then we can do, from this point, we can draw so if you draw a horizontal line here, that line will cross with equilibrium, right, curve. Then you get a point. From that point, you can read the, composition x1, right? And then you draw a vertical line there. It will cross with operation line again. You will cross the operation line, and you can read the y coordinate of that point, right? Y2, x1. From last lecture, we basically discussed when x1, y2 are the composition here, right? Below stage 1, but above stage 2, right? Again, how do we do that? Basically, x1 is in equilibrium with y1, right? So when we know y1, we can get x1 on the equilibrium curve. Then y2 is on the same operation line as x1, right? So now, as we know x1, then we can find y2 on the operation line, right? So now we figure out the composition above stage 2. And if you do this, continue to do this, right? Draw a vertical horizontal line here that cross this point, right? You read x2, then you draw a vertical line that cross the operating line. You read y3, right? And that's going to be, the composition below stage 2. Right? So just continue to do this. Then at stage n, you will get a composition. Ideally, this composition will match the composition below, n stage, right? Exactly match that. That's the ideal case, right? As we show here. In this case, in this particular case, that's stage 1, stage 2, and stage 3. As you, and finish stage 3, you will reach a kind of like gas phase composition yn+1. That's that, and you will reach a liquid phase composition xn. That exactly match with the composition below the n stage, right? That's the ideal case. So in this case, we only need 3 stages, right? Stage 1, stage 2, and stage 3 to achieve this desired separation outcome. So what if when we do this, but this line does not cross, so this line cross a point that's above yn+1. What does it mean? Okay, so basically let's recap. Like the whole process of doing this graphical method to figure out how many stages we need is, first you locate the point for the solvent feed x0 and desired y1 on the graph. That's this point. Then you determine the operation line, right, from v prime to l prime, right? If you know l prime, v prime, you know the slope, then you know x0 and y1, so you can draw this line. Then you can do this step Marshall process, step horizontally, then vertically, horizontally, vertically, horizontally, vertically, right? Until you find a point that falling on the operation line, or it's above the operation line or below, above the operation line. Okay, then you can call a victory. You can declare a victory. Okay, now let's look at this case. What if, in this case, so we have a the liquid flow rate is only 2 times of the minimum liquid flow rate, right? So we have a slope here. Then we can repeat the process we just did, starting from the the bottom point, sorry, the top point on your top of your absorption tower, but it's the bottom point on your operation line, right? Then you do this march off horizontally, then vertically, right? Horizontally again, cross the equilibrium curve, and vertically. Right? Now in this case, as you can see, I have to extend the operation line to outside this figure so that I can find where this vertical line cross with operation line, right? At that point. And that point will have a y composition much higher than this, right? So that means with 2 stages, we can achieve the desired separation outcome. But this 2-stage tree tower will have kind of like some buffer volume to treat a feed composition with even higher more amount of solid, right? That is defined by the y coordinate here, right? So even though in this case we only feed a gas with this yn+1 composition, but even if you feed more, we can still achieve the desired separation outcome with just 2 stages. Okay. Right, because that point just determines the maximum kind of absorption power of your absorption tower. Now let's look at another case. Right. So in this case, if we choose operation line 3, that's with an even lower flow rate of liquid absorbance. You can do the same, from this bottom point at your operation line, do the march-off, horizontally cross with equilibrium curve, vertically cross with operation line, and horizontally cross with equilibrium curve again, and vertically. And as you can see, this is similar to the previous case. You will only find this line will cross with your operation line with a point that's higher than that point. Right? So then, in this case, even for a state absorption tower with 2 trees, the tower has extra kind of like process capability than yn+1. Right? We can do it with 2 stages. Now let's look at another example. If we further reduce the flow rate to operation line 4, what would happen, right? Remember, operation line 4 is the minimum absorption rate in which the operation line will cross with equilibrium curve at this point, right? Similarly, you do this march off, horizontally, vertically, horizontally, vertically, horizontally, vertically, right? What you will realize is that because now, as you can see, these two curves, they cross at this point, right? When you do this march off, you can never get out of this enclosed region, right? Because there's no, unlike in the previous case, for example, for the operation line 3, you have a kind of mouse between operation line 3 and the equilibrium curve, right? So when you do the march off, you can go out. But in this case, because this mouse is closed, and then you do this many, many times, and eventually you are going to reach this point. But you have to do it in series with infinite amount of stages in order to reach that point, right? So you have to use infinite stages to reach that point. So what does that mean? Physically, that means because you are operating at a minimum absorption flow rate, right? And we know minimum absorption flow rate means that when the liquid absorbance comes out from the absorption tower, it's saturated with the solid, right? And we know that before your liquid absorbance is saturated, it has this capacity, and that capacity to dissolve the solid. That capacity is basically drives the mass transfer of the solid from the gas phase into the liquid phase, right? But now you just don't provide enough kind of like driving force for doing that. Then you have to increase your number of trees to give it enough time for this mass transfer to happen, okay? Whereas if you operate at a higher flow rate, then you have plenty, in your liquid absorbate, you have plenty amount of, capability to dissolve your dissolve your solid. Then you only need a limited amount of, trees to achieve the desired operation separation outcome. Okay. So that is to say, does a tree exist between liquid flow rate and the number of stages, right? If you have a larger liquid flow rate, and you need less amount of trees to achieve the same separation outcome, right? In other words, there's a trade-off between operation cost and capital cost, right? If you operate with a larger liquid flow rate, then you have a higher operational cost. But that requires less number of trees. So when you design your absorption tower, it requires less capital cost. Okay. So you can also do this algebraically. The way you do this graphical method by computer. So first, we know x0, y1, and L prime over v prime. That's a slope, right? Then you can from k1 you can solve x1. Then you can find y2 from the operating line, right? Just plug in the numbers, right? Once you know x1, and just plug in all the numbers into this equation, you can get y2. Then you can solve x2, then etc. Right? So basically, this is just like what we did graphically. So this step is to basically find this point. Step 1 is find this point, and step 2 is do this vertical march off and find this point, and you do this, repeatedly. And in this case, you need to have a model for your key value, right? And if key value is not a function of composition, right, that's the case in which once we know temperature and pressure, you can find out key values, right? You can just do this process. But if key value is a function of composition, then basically what we're gonna do is just similar to what we discussed in our last lecture. Then you have to do some iteration to find out k first, right? once you find out a key value, then you can do this. Okay. So let's look at one example. So this example is from your textbook, and it's about recovery of alcohol from a like a mixture of alcohol with some other gases, right? So basically, in a bioprocess, this molasses is fermented to produce a liquid containing ethyl alcohol. Okay, we have a CO2-rich vapor with a small amount of alcohol evolved. Now we're trying to recover the alcohol from this CO2-rich vapor by absorption with a treat tower. Okay? Now we need to determine the number of equilibrium stages required, okay, to achieve the desired separation outcome, right? If we operate this system at a constant temperature and the pressure condition, and we assume again only the alcohol is transferred, is absorbed, right? So let's say if the entering gas is so that's our absorption tower, and we know the flow rate of the gas feed, right? That's V here, and we know the kind of like this is the mole fraction of your solvent in your gas phase, because it's alcohol vapor dissolved in CO2 gas, right? So that's 98%, which means your alcohol mole fraction is 2%, right? At 30 degrees C and 110 kilopascal. Your entering liquid is pure water, right? So that means X0 is 0 at the same temperature and pressure. We require the required recovery is 97%, right? So here the required recovery 97%, that means you have 97% of your alcohol going into this gas stream, and only 3% going out, leaving this absorption tower in the liquid absorbent, phase, right? First thing you do is find the equilibrium curve, right? So here we use modified Raoult's law, and you can find the key value, right, to be that. So next thing you do, you need to find the operation line, right? To do that, you just need to compute these parameters. So first, we compute the solute-free vapor phase flow rate, right? That is basically the mole fraction of CO2 multiplied by the total flow rate. That gives you this number. Then you get the liquid phase, the minimum liquid phase solute-free flow rate, right? Just plugging the numbers here. So from this equation here, right? So we know V prime. We just need to calculate L prime mean, right? And here we know these numbers. Yn plus 1 is 0.02. So we know all the other numbers. And we know the key value is 0.57, right? And we have 97% of recovery. Then you can get this. And if we say we're going to operate this tower at 50% above the minimum flow rate, right? Then L prime will be 1.5 times of that. That gives you this number. Okay. Then alcohol recovery 90% means that in the feed composition you have 0.02 multiplied by 180. That's the total flow rate of your alcohol. Then 93% of that will end up in this stream, right? Then 3% will end up in this stream. Okay, that's 1 minus 0.07 multiplied by these two numbers. Okay. Now we can determine the alcohol mole ratio at both the ends of the operation line, right? So basically, we just need to figure out the alcohol mole ratio. Alcohol is a solute here. We need to figure out mole ratios of alcohol at here and here, right? So at the top, X0 is 0, right? That's given. Y1 is basically this, right? That's the amount of alcohol in the exciting gas stream divided by the amount of CO2 in the exiting gas stream, you get this mole ratio. Similarly, you can do you can compute the mole ratio entering the tower in the gas phase and the mole ratio leaving the tower in the liquid stream. Right. Now you have all these numbers. You can find the operating line. Okay. So plug in the numbers into this equation. That gives you the operating line. Okay, which is plotted here as this straight line. Then you can calculate the equilibrium curve basically by plugging the numbers into the equation for key value, right? So we know y and x and here. We know key value. Just plug in there. Then rearrange this equation so you can write it as y as a function of x. Then you can plot it here. Right? That's the equilibrium curve. Now we have the operating line, we have the equilibrium curve. We can do this step function to figure out how many stages we need, right? Starting from x0, y1 at that point, you march horizontally first, then cross the equilibrium curve. You march, then you march vertically, right? That's stage 1. Then you do this repeatedly, right? Stage 2, stage 3, stage 4, and etc. Right? Until you reach a stage, and then if you look at the composition of the gas phase in that stage, that composition will be higher than our incoming composition. Then you can declare a victory. You can stop there, right? So basically, for this process, for this example, we require 7 stages, right? Actually, you only need like 6.1 stages, but because the stages are integers, you cannot do fractions, so we have to do 7 stages. But with such a design, in theory, your absorption tower can handle a gas composition that is much higher than yn+1, right? It can handle a gas composition at that point. Okay, so we can stop here, and on Friday we will continue on packed tower design.